Hi everyone, today we'll hear Minoo present on self-training with noisy student, and we'll see if it improves or not.
Yeah. So hello everyone, and thank you for joining this lecture today. And today I'm going to talk about self-training with a noisy student improve internet classification paper, which is published in 2020, and the author proposed a self-training method for ImageNet classification. They achieved 88.4% top one accuracy, which is outperformed the previous state of art by 2%. These are the content that I'm going to cover. The paper introduces a noisy student approach to training model. Unlike traditional supervised learning models, it uses abundant unlabeled images for training, and this semi-supervised method extending self-training and knowledge distillation, which is performed on out of distribution images with only a small part of that being from the same distribution. And so the majority of the images, a large fraction of it is from out of distribution sources, and only the small part of it is from the image belonging in distribution images. So this approach enhances the accuracy and robustness of image model and make it better for handling the diverse data. So we need to know about the knowledge distillation first to move further. In the knowledge distillation, it's a technique that we use for transferring the knowledge from a larger pre-trained model to a smaller model, which is we call it student models. This process involves training the student models to mimic the behaviors and predictions of the teacher model. And so the teacher model is a large pre-trained model with a lot of knowledge, and the small one is smaller one with a less complexity, and it's the one that we want to learn to train. In this process, only you can say that the back propagation will happen in the in the small models. So both of these models have the softmax function. The teacher model is used to train guide the training to the student model, and the goal is that we want the student model to produce similar outputs as the teacher model. Both of them produce soft labels or predictions using the softmax function. Soft predictions are probability distributions over the classes. The distillation loss that we have is a loss function used to minimize the differences between the soft predictions of the teacher model and those of the student model. It actually encourages the student models to learn the underlying patterns and relationship which is present in the teacher model's prediction. And the student model also produces the hard prediction, which are discrete class labels, and we kind of compare them with the ground truth. The student loss is another loss function that they use. It minimizes the difference between the hard predictions of the student model and the ground truth. The total loss is the combination of these two loss, the distillation loss and the student loss. And the soft prediction plays a significant role in this algorithm.
Excuse me, can you go back? What's the point of a teacher model? Is it a pre-trained model?
Yes, it's a pre-trained model.
And why you don't just fine-tune it on a new task? Instead of training in a student model?
We kind of trying to use the smaller models instead of which is it's more simpler.
But I can tell you, the great marketer, Jeffrey, come up with or educator, he came up with like a very good explanation of what is happening. He called it dark knowledge. So when you start training a model to the hard label, basically all you have is an image and a label. You have a binary string, all zeros and only one thing. It has to be a chair. It has to be a cat. It has to be a car. But then after the model trains to do everything perfectly, you notice that if you put the soft labels and sort them, say, then the model knows that a chair and a cat are similar. They have 4 legs. Their scores will be, even if the model is looking at a cat, the score of a cat will be high, but next one will be a chair, not a flower, and etc. There is additional knowledge that is not in your labels, the structural regularities that the model has to extract painfully before it starts to be good. So your teacher has already gone through that pain, and that's why the soft labels, you're training your student to track the teacher's distribution, that hidden knowledge, that regular relationships between those categories. That's an additional, so and then it trains faster because of that. Go ahead.
So here I explain more about the soft and hard labels. Soft predictions are generated using the softmax function, and the softmax function computes a probability distribution over the classes for a given input. The function's output assigns higher probability to the predicted classes and the lower probability to the other classes. And the temperate parameter T is used in the softmax function to control the distribution's sharpness. And a higher T value results in softer probabilities. However, a lower T value produces a sharper distribution. The hard labels are discrete class labels. For example, here that we have dog class, and we don't have any information about other classes here, and we don't know how the dog class is related, for example, to cat classes. But in the soft labels, the probability distribution over classes is kind of calculated, and we have it as an output. And they provide more information about the relationship between the classes. For instance, this soft label not only indicate the high probability for the dog class, but also it suggests that it has some similarity with the cat class as well. So the self-training and distillation method has 3 main steps. First, they train a teacher model on labeled images, and then they use the teacher to generate pseudo labels on unlabeled data. And then they select top scoring examples. They choose unlabeled examples with predicted labels that exceeds a certain threshold, and then they kind of train a student model on both of these data, the pseudo labeled ones and the labeled ones. The noisy student approach that this paper uses is an extension of the self-training and distillation method in two ways. The first one is that they introduce the noise to the student model during training, and they use three types of noise: data augmentation, dropout, and stochastic depth. And also the second difference that this model has is that the student model is allowed to be larger or equal to the teacher model, which it wasn't exist in the previous model, in the previous approaches. This is the algorithm that the paper explained. In the context of noisy student training, the requirement involves using the labeled and unlabeled images. Initially, the teacher model is trained to minimize the cross-entropial loss on the labeled images. And then the noisy teacher model is employed to generate soft and hard schedule labels for unlabeled images. And then the student model is trained and aiming to match to the teacher model's capacity. And this student model minimizes the cross-entropial loss for both labeled and unlabeled images with intentional noise. After that, the student becomes a teacher and initially returns to the second step for iterative process, which will converge to the result. Or it will converge to some kind of point that we kind of specified with the result.
Can you repeat like what student becomes a teacher, like that part, or did they?
Because the model can get even bigger than teacher, if it performs better than teacher, they kind of replace it. Because it's going to train the next model. And the architecture, I think that will explain a lot here. I have enough part.
And there is a question online as well, I think. That you.
Yeah, it's from Nan. I just wonder, like, since they're just reiteratively training the model, what's the purpose of separating the student model from the teaching model? If they just have one model that's iteratively training, and how that's gonna be different from like having a student model here?
The teacher model is going to, it has some kind of knowledge that it's going to pass it to the student. And the student is kind of adding something to that knowledge and to pass it to the next student.
Yeah, so I wonder what if they just have used one model that having this feature that can like keep adding new features to the next iteration of the model. Would that be somewhat?
So
If you use only one encoder, you have like the features that trained it already. So your loss will be like already good. So model won't learn anything. And the main point is that you train kind of bigger model first, like call it teacher, and then you and train the small model, which called student.
And
In this sense, you kind of are going to kind of learn a new model, but which not too far from the teacher model, but in the same time using kind of some knowledge of the teacher to define the loss function.
oh,
So it's kind of,
so really this is just a terminology issue, like for each iteration, like for iteration one, the student model is the teacher model of the next iteration. Is that the situation?
no, it's not
No.
just terminology, like, because if you have different encoder, like teacher and student have different neural network, and they have different weights. And because they have different weights, that allows you kind of to have the learning signal. You kind of want your student to predict the teacher. At the same time, you want to solve the task you want. So it's kind of in some form like regularization.
Hmm.
And distillation is also soft. It's kind of trying to use distillation law to predict on a kind of distribution level. It's not like hard task, like, for example, you want to predict the head from the image, but your student is forced to predict kind of distribution of this outcome to match the prediction of the teacher.
Okay.
But like all this works just because of stochasticity. You have different epochs, they like have different stochastic initialization, but teacher usually train it on something.
But even from what you're saying, at least what I hear is that we want to avoid getting stuck in the local minimum feature, like low-level representations. So we want, for example, if the model learned wrong low-level features, but it is able to capture the loss correctly, it has information in the loss, kind of in the high-level representation. But your new model, by trying to mimic high-level representation, is not constrained by low-level features of that model. It may be able to add better feature set and even surpass this model in the representation at the high level, like your global representation could be even better.
This is
Yeah, I see.
big point.
I see. Okay. Thank you.
But there are like different approaches how you can do it. Like, for example, instead of like teaching a student, some people just create the expand, like they create a second encoder, like second copy of a teacher, for example, and you can kind of accumulate your weights using exponential moving average of your teacher weights. And there's like multiple.
We still need to check how it works.
Yeah, that's not a lot of work that have been done on top of this.
The culture here is just plunging and interrupt when you have a question. Usually no one is looking at the, I just happen to see your hand raised, but usually we just interrupt each other and discuss, and you're new as well. Welcome to just interrupt and join in this discussion with anyone.
So does it means like the teacher model is like a parent model always being here and being implemented for the whole process, whereas the student model is the one that keep iterating?
Oh, you mean the frozen? Is teacher frozen?
No,
Or?
it's kind of, the models is kind of subsequent and it grows by each step.
I think it's not frozen because this is not pure distillation. In pure distillation, you froze it.
Well, look at step 3. Learn an equal or larger student. So you take a new model which is larger than before, and but the one that you already trained is frozen now. And you train a new one that is larger. Then you freeze that one, promote it to a teacher, create a larger model, and train it. And at least that's my reading from this slide.
Okay. Thanks.
I think the teacher model should be frozen, otherwise, over the iterations, the performance of the teacher model or the reliability of the teacher model can diminish, right?
Yeah, but it looks like we retire the teacher, like, and promote next model to the teacher, and actually kind of go in a paper. Well, anyways, let's see. Yeah, I agree with you. If we use the same teacher, then yes, then we can.
I think if you cross it's just like too hard to control, like maybe you still can unfroze the teacher, like a two-step approach of training, like you cross the teacher, then you cross the student and adjust the bit, for example, teacher. Because this technique can be used to like step the labeling approach, like you might be like able to kind of churn something on and like freeze teacher or freeze student and like.
But until the student achieves a reasonably good performance, we cannot do this switching, right?
I think you can, because right and self-supervised uses such things.
But is convergence guaranteed, and then like you can get to a fixed point, like in a loop and just back and forth, oscillate without converging. If you like, you need to kind of enforce convergence that it will keep getting better in some direction of it.
Because you can, example, if you not keeping frozen both side, like people can use like slope gradient to froze one side, but because usually loss can be like symmetry side, you can have like two components of the loss function where in one part you freeze a teacher, in one part you can freeze a student, but you have two loss function. But when you compute this loss function, gradients don't flow from each loss function to each other, so you use like slope gradient treatment. And then you kind of can control this cases and create collapse of representation, because if you can switch two things at the same time, of course it's easier probably to find solutions that will destroy everything. You can just do intensity, right? So maintain.
Continue.
So this is a figure from the paper, which explains the algorithm. So we have it, we train the teacher model with label data, and then we infer the pseudo labels on unlabeled data. Then we train the equal or larger student model with the combined data, and we add the noise as well. And we make the student a new teacher, and we iterate this process until convergence. These are.
Can we see the previous slide again? So, you have a teacher and then you are training a student and make the student a new teacher. So who will be the student again? Who will be the next student? You will create a new student
model.
again?
Yes.
Equal or larger student model, so that's a new model.
Yeah.
From scratch.
Now make the student a new teacher and then what?
Train equal, look at the left box, train equal or larger student model.
Okay.
You create this new student from scratch that is larger than before.
So this is the noise that they introduced to this data. There is a rank-based data augmentation is employed to augment the images. The goal is to ensure that the student model produces consistent outputs for both the original and augmented data. And we drop out the neurons are randomly dropped out of each iteration, which is contributes to assembled-like behavior. And this helps the student model's robustness and generalization. And with the stochastic step, they enhance the ensemble data behavior of the student model as well. So the careful handling of the data balancing helps to maintain the fair representation from each class. So they use data balancing as well to ensure that the training process is not kind of leaning toward certain classes due to the amount of data sets. And they discuss the comparison between the continuous soft distribution of the total labels and the one-hot encoding approach, which in this figure they show that when they use the soft soda label, the accuracy is higher. This is the architecture they use, which they use the EfficientNet, which is the basic model, but then but they scale up at each iteration. And so we have different size of models here, and the architecture of the teacher model and the student model may be the same or different. The student model needs to be bigger enough, as you can see in this figure.
Yeah, what is like, what are these circles? What is the color? What does it indicate?
Yeah, this is the architecture that this paper used. This is the teacher model, which is then go to the student model, which is the bigger one. And then it replaced this model as the L1.
Each circle is a model.
Yes. Each
So it's
circle-
not model architecture, it's just,
It's the architecture that they use to manage the.
okay, they start with V7, whatever that is, then go to train L0 using that V7, train
Yes.
L1 using that.
And in each step, the model is equal or bigger than the previous model, because the student can be equal or bigger. And they use the efficient network.
So the architecture inside of the circle is efficient,
Yes,
which is a CNN transformer, or what is efficient?
it's, yes. This table indicates the accuracy results. It displays the top 1 and top 5 accuracy for both the NOSI student training model and the previous state of art model method. And they also reported the number of the parameters here. This plot is about the size of the model that is scaled up. The NOSI student training for EfficientNet without iteration, because of the computational cost, they just not use iteration. And this image can show that the NOSI student leads to the consistent improvement of 0.8. I mean, there's a typo. And the authors evaluated their models based on, they kind of separate the data set to 3 different sets to evaluate their model. The ImageNet A is focuses on adversarial images, and ImageNet C is generate the distortions like blurring or fogging, and the P is involves the rotation and the scaling. So in this image, they kind of compared these 3 data sets and their results on each data set. This is overall accuracy that they have for each of the ImageNet data sets, A, C, and D, and the overall ImageNet data. And they also compare it with the previous state of art models, and they can show that their accuracy is good. These results are, it's the more detailed results on each data set that they produce. For the ImageNet A, this is for ImageNet C, and this is for ImageNet B. So in conclusion, this paper approach a good results. It increases the accuracy and the robustness of the model in comparison to the previous approaches, and this new method kind of doesn't need the increasing amount of data, which is kind of good. Thank you for joining the paper.
So any questions, any other discussions, anything? Or any of your observations, why this paper is interesting or?
Yeah, I think this paper is kind of did a good job because when the data is, most of the semi-supervised learning, the algorithms are depend on the number of the data, and when the data is increases, they perform better. This is, I think that is the good one. It doesn't depend that much on the data, number of data.
So it doesn't need more data, like they're reusing the same data trained, that's what you mean, right? It's just the model.
In the comparison for the other semi-supervised learning methods that I looked through, I think this one is kind of more successful.
And is this a recent paper,
It's
2020?
2020.
Okay, so what was there follow-up work, do you know, anyone done anything on top of that? Because recently there was a paper like that, I tagged you in a deep learning channel, I think. With language models, large language models that are used in a similar fashion. One is training another. It's not auto GPT though. So my question is about follow-up work. Was there any, do you know if anyone cites this, or did they publish next result on that? No. Oh, anyone has questions?
Can you show the slides with bar? I guess it's what's good. I just don't quite understand what is noise in honesty.
This is the noises and the difference that it has. We have a self-learning and distillation methods, and this model is kind of uses the same structure, but it adds some noise to the model.
Okay.
This is it has two differences with the self-training and distillation methods. Their paper. The first one is that they introduces the noise to the data set, and second is that their data can the model can be equal or bigger than the teacher model.
So there is another paper on arXiv, recent paper, reinforced self-training for large language models. I posted it in Zoom Slack, but I also posted it in Zoom chat, and I posted it on Slack. It's the recent paper by Reno founded. So people are working in this direction. Okay.
I guess if there's any time, I have some like.
Yeah, tons of time.
So basically, it's kind of comes to mind is it's kind of like a GAN where, but it's like there's like the teacher, like it seems like the discriminator and generator are kind of like swapping roles or something.
And in GAN, they kind of generate the data, but as far as I know.
Yeah, so they're not generating any data.
They kind of transferring their knowledge to the student model.
Okay, so there's still a real
They're
data set,
dealing with
there's no
models.
synthetic data. Okay.
Does the teacher train on noisy data? Or only the no? And when we kind of added the noise to the data set, no, yes, in Canva. in an indirect.
Are we adding, can you go to the formula, are we adding the noise to the data set? I thought we were adding the noise to the object, to the loss or representations,
Yes, yeah.
yeah, F noise, so that's the data, right? What is F? Yeah,
Okay, so I think the first teacher does not train on noisy data set,
Yes.
but then all of the subsequent teachers, which were previously students, were trained on noisy data somehow.
but I don't know what is F, they don't define it. Or do they? Images with noise added to the student model.
And probably noise labels, that means that they detected by the teacher. Because they do like certain labeling of the unlabeled data.
This is why tilde is that, yes, but then it also images with noise. So if you look at the last line, y sub I without tilde is the true labels, and y sub I with tilde is the labels predicted by the teacher. But then F noise is what? There is another, like, it's an encoder, or this I don't understand, because it has parameters, data as it takes X as parameters. If it's just adding noise to the images. So there is this data, this F noise thingy has parameters. Is it does it produce an embedding then? Or what it's doing?
But I think they had some about data limitations, they had specific data limitations.
I didn't see the paper definition of F. Well, frankly, nothing is defined.
This noise is added, so where's it added? Does it say?
To the data, to the images,
Okay, then.
not added
I think it adds.
images with
new
noise.
data set that we are.
I mean, that seems like effectively what that does is adds some sort of like, margin, or just, like if you look at the decision boundary, think of this as decision boundaries, then it would expand the decision boundaries to some extent. To not be so sensitive to in distribution training. By adding noise.
But we're kind of guessing.
So there are two things, there is a input noise and model noise. Input noise is just random methods, they just use random augmentation. For model noise, they use stochastic depths and the other thing.
Yes.
Yeah, so like the paper is super unclear. When the student is deliberately noised,
No,
what happened?
in noise by augmentation and
Oh, by augmentation, you can add random noise to the weights, the parameters. You can do so many things.
no, they don't do anything else. They only do data augmentation and stochastic depths and dropout. This is definition of noisy student.
Just drop out. What is the other one? Stochastic?
Stochastic depths.
What is that?
It's basically you randomly dropping layers. Like you're not getting embedding from all the layers.
Mm,
It's like what is meanwhile trying to do.
not really, but okay.
No, it's really. If you check page 2, there is a section called noising student.
Yeah, that's what I'm reading, and it's not making things clear. Yeah, so dropout and stochastic depth functions are used as noise.
Seems like this is basically, just. Regularization, but yeah.
But from a case perspective, saying noisy student is better.
I mean, it's philosophically satisfying, but the name of the paper.
And look at my image in the general channel to illustrate this paper. It's kind of marketing. Oh, yeah. Okay.
I mean, unfortunately, being good marketing is important.
Yes, it is.
I think MeshNet would have taken off the MeshNet names, like just like MeshNet, because people like, you like,
No, actually people also, when MeshNet called MeshNet, they got they think about meshes, but
That's true. It can be used for that though.
or anything. Even brewing coffee. Behaves like a single model. This I don't understand, but okay. Noisy students, so they kind of shake up the student quite a lot. Augmentation is an important noising method.
so it's like multi-view self-division and damaging by,
Dropout.
yeah. I think we was trying to do something to their son.
Yeah, I don't know also why filtering is so important, why it's so sensitive to the filtering and balance. It's the next section, and what you said, it has to be exactly balanced, but why? Why it is so sensitive? Unclear, because long ago, 2018 or something, there were papers that claimed that the networks learn to the networks learn the balance of the data set. Like they add additional weights. I forgot what the process is called, but for training deep learning, you don't need to worry about balancing at all. That it's kind of, and I can dig those papers there were quite convincing demonstrations of what is happening. So that's why I'm reacting is kind of why it would be fragile. I mean, not enough parameters. No, but they're growing at large. It will learn the balance. Okay, like probability distribution. This is more likely to be standard. Okay, thank you, and let's stop the recording here. Thanks everyone.